Hello, my name is Yutao. I am a PhD student at Johns Hopkins University, and I'm very happy to present our paper, Semantic-Aware Video Representation for Few-Shot Action Recognition. This work is in collaboration with Dr. Béjar and Dr. Vidal. We have achieved a lot of progress in general action recognition with the development of deep learning methods. The action recognition is typically achieved using traditional supervised learning techniques, which requires tons of training data and operates on a fixed set of action classes. In sharp contrast, humans are very good at using similarities to recognize new classes with few examples. For instance, looking at the first row, you would know these two videos belong to the same action category, namely playing the piano. So does the second row. They are also the same action, namely playing the cricket. However, looking at the third row, you might have never seen the action in the left or in the right before. But as humans, you can quickly tell they are different actions. That's the idea that humans use similarities to recognize unfamiliar actions with very few examples, while most of the deep learning methods require a lot more to achieve a similar performance. Additionally, there are certain scenarios where collecting abundant annotated data for each action category is impractical or very costly. For example, collecting symptomatic videos of patients with a rare disease. This is where few-shot action recognition comes in. It is an example of meta-learning and shares the same idea of learn-to-learn. It operates with only a handful of examples per class, which mitigates the data scarcity problem. Moreover, it can also generalize well to unseen categories during testing phase. Here is an example illustrating how few-shot action recognition works. Suppose we want to know what action is performed in this video. Instead of letting the model learn on a lot of videos in the same category, we provide the model with a series of flashcards consisting of various actions. Then we ask the model to find the most similar video in those flashcards. Specifically, we can use an arbitrary similarity function to compute the similarity scores between videos, followed by applying the softmax function to obtain the probabilities. Finally, we classify the question video as the one with the highest probability. Under the few-shot learning setting, we refer to the question video as the query set, the flashcards as the support set. The whole process we went through is called an episode or a task, which is formulated as an n-way k-shot problem, where n refers to the number of action categories and k refers to the number of samples per category. In order to compare the support and query set, we need two key ingredients, namely feature extraction for the videos and an effective similarity function to measure the similarities between videos. In this work, we focus on the first one, feature extraction. Now, there are two key challenges regarding the feature extraction in the few-shot action recognition field. The first one is concerning spatial temporal features. Advances in the general action recognition indicate that spatial temporal feature extractors compared with frame-level feature extractors are more promising and can extract more discriminative features. However, most of the current few-shot action recognition methods still rely on frame-level representations. As a result, they often require additional components to model temporal relations and to achieve alignment of these representations. In this work, we directly leverage a spatial temporal feature extractor, extracting more discriminative features and avoiding the need of extra components. Another challenge is that the current trend of research has been exploring multiple modalities, with a particular emphasis on the integration of video and text, as their features are complementary to each other. However, existing few-shot action recognition methods often struggle to effectively integrate textual semantics. Some methods perform only fusion, for example, addition or concatenation of features from different modalities without aligning them. Some other methods align the features from different modalities, but they don't fuse them after alignment. In this work, we achieve both alignment and fusion of the visual and textual features in a compact way. In summary, our contributions are threefold. First, we propose a semantic-aware few-shot action recognition model named SAFSAR, which leverages a spatial temporal feature extractor. Second, we design a novel paradigm for aligning and fusing visual and textual features in a compact way. Specifically, we propose a multi-modality fusion module to adaptively fuse the textual features into the visual features of the support set, while the query features remain untouched. Moreover, in the end, we will be associating semantic-unaware query features with semantic-aware support features, which aligns the features from different modalities. And finally, we achieved the state-of-the-art performance on 5 benchmarks. Now, let's dive into more details of our model. Just as illustrated in the previous example, we have a support set consisting of various videos and a query set of which we don't know the action category and want to find out the most similar one in the support set. First, we use video MAE to take the videos as input and extract spatial temporal video representations. Additionally, under many shot settings, we just use the averaged representations in the same class as the class prototypes for the support set. Next, we propose a multimodality fusion module to integrate textual semantics into the video representations. Specifically, this module takes 2 inputs, namely the class prototype from the previous step and an elaborative textual descriptions for this class. The descriptions are exemplified here for brush hair and golf. They are detailed explanations which contain both high-level semantics and nuanced aspects for actions. Then, we tokenize these textual descriptions, which is then passed through the BERT model to get the textual features. Following this, we concatenate the class prototype as an extra token to the textual features. This concatenation is then input to the fusion transformer to get the semantic-aware representations. Next, we have a task-specific learning module. It consists of 1 transformer layer. It takes the support and query representations from the previous step as input and outputs task-specific representations for them. This module aims to augment the video representations via cross-video interactions and prevent the features from overfitting to irrelevant background information. Finally, we compute the cosine similarity scores between the support and query set, followed by applying softmax to get the probabilities. And eventually, we use cross-entropy laws to train the model. We conducted experiments on 5 benchmarks under 5-way, 1, 3, and 5-shot settings. The results show that our proposed SAFSAR achieves remarkable performance and consistently exhibits substantial advantages over other state-of-the-art methods, especially under the challenging 1-shot and 3-shot settings. Specifically, SAFSAR provides around 11% and 14% absolute improvement in SSV2 full and SSV2 small benchmarks under the most challenging 1-shot setting. The superior results demonstrate the effectiveness of our approach. We also conducted a qualitative analysis on the semantic consistency. These 2 figures show the extracted features without adding any textual semantics for HMDB51 and UCF101 benchmarks. Now, after employing the multimodality fusion module, we observe the boundaries among different classes become more expanded and the classes are better separated. We believe this indicates effective introduction of semantic consistency into the features. In summary, we proposed a multimodal SAFSAR for the few-shot action recognition task. It leveraged a spatial temporal feature extractor video MAE and employed an efficient transformer-based multimodality fusion module for adaptively integrating textual semantics into the video representations. We conducted extensive experiments on 5 benchmarks and improved the state-of-the-art performance, which demonstrated the effectiveness of our proposed model. Thank you.